Hello, my name is Roman, and I will present our joint work with Edmond and Jakob about flow-based generative model for point clouds. We study deep generative models for 3D data. Our aim is to design a model capable of producing 3D shapes given samples from a latent shape space. Such models are not only interesting in the context of generating plausible novel 3D shapes, but also can be used to extract features from data in an unsupervised way when provided with an encoder. Moreover, it can serve as a basis for conditional generation problems, for example, single-view reconstruction task or shape completion. In this work, we implement a probabilistic hierarchical latent variable generative model, which captures point cloud distributions with the help of conditional invertible normalizing flows. The choice of the 3D data representation plays the defining role in the design of the model architecture in 3D data generation. The first methods applied 3D convnets to generate voxelized shapes in a GAN setting. Although straightforward, such approaches suffer from cubic scaling from the output voxel grid resolutions. First generative models for point clouds combine an MLP-based autoencoder with a GAN operating on the latent space of the autoencoder. The main drawback here is the hand-wired number of output points, defined by the size of the last fully connected layer. One of the first mesh-based modeling approaches applied graph convolutions to capture phase appearances and expressions. A major limitation is that it requires all meshes to be in dense vertex correspondence. Thus, all meshes need to share the same topology. Recently, implicit function representation was adapted for 3D shape modeling with deep networks. Although powerful, to show its potential, this approach requires sampling on a high-resolution 3D grid and optionally additional post-processing steps, namely Marching-Cube's algorithm, to convert volumetric occupancies to meshes. Despite the lack of full shape geometry, compared to other extrinsic and intrinsic representations, point clouds are the most scalable, which make them a natural 3D data representation for many 3D capturing methods, including multi-view stereo and range sensing. In this work, we continue to explore efficient modeling of this 3D data modality. Generative modeling for point clouds was studied further after the latent GAN models. AtlasNet approximates shapes with the collection of parametric deformable surface patches. It mitigates the limitation of fixed-size point cloud outputs and shows excellent autoencoding results. However, due to surface patches not being connected properly, densely sampled point clouds from that model show reconstruction artifacts, such as self-intersections and sharp erroneous edges. Point cloud GAN was the first work that linked point cloud generation to a probabilistic hierarchical latent variable model and applied a variation of Wasserstein GAN to capture point distributions. Finally, most relevant to our approach is point flow. It relies on the same hierarchical latent variable model, but unlike GANs, it uses likelihood-based training. Point flow uses continuous invertible normalizing flows to construct a flexible density on 3D points given a latent shape vector. The main limitations of this approach are the high computational costs to train and sample from the model. Both processes require solving ordinary differential equations, which is done through numerical solvers. Our work is based on the same probabilistic model and shares the overall structure with point flow. However, we substitute continuous normalizing flows with one of the most established and efficient discrete normalizing flows, affine coupling flows, and redesign them to support conditioning. Moreover, we extend the approach to the single-view reconstruction task. First, let us discuss the probabilistic model. Point clouds are unstructured sets, which means that each point distribution must be invariant to permutation of point variables. Definitive representation theorem states that such distributions can be factorized, conditioned on a common latent variable. In case of point cloud modeling, samples from this latent variable z can be thought of as elements of abstract shape space, which captures possible shape variations. Given the latent variable, all points are sampled IID. Hence, the model admits point clouds of arbitrary cardinality. As is common for latent variable models, we can mitigate the intractability in the integral by relying on a variational lower bound, as in VAEs. In our case, the inference network produces an approximate posterior distribution over the latent shape variable, given a point cloud. The main remaining challenge is to design the conditional distribution P of x given z on 3D points given the latent shape. Here we show an overview of our model. We predict approximate posterior distribution by a PointNet type inference network from an input point clouds. During training, samples from the posterior condition-based distribution of point flow and all the affine coupling transformations. Complete model is trained with the obtained variational lower bound for the log likelihood. During generation, conditioning uses samples from the latent shape prior. In this overview of our model, you can see how the proposed discrete per point transformations warp the points sampled from a Gaussian-based distribution. Now we present the proposed conditional affine coupling flows. For each point x in a point cloud, we consider a latent variable y of the same dimensionality. This latent variable is firstly sampled from a base Gaussian distribution with parameters inferred from the latent shape. The flow is constructed on top of that sample by applying conditional transformations. First, the latent variable dimensions are divided into two groups, kept and transformed. Then, kept transformation dimensions are fed to an MLP, which inflate the feature dimensionality. A separate MLP predicts conditioning coefficients for the inflated features. After scaling, they are fed to an MLP which deflates the dimensionality to match the size of the transformed group and predicts the parameters of resulting transformation. To properly capture point cloud distributions, we perform proposed transformation multiple times, 64 transformations in this work, alternating among all possible partitionings of 3 dimensions. The final transformation is considered to return point samples from the data distribution. Using the change of variable formula and invertibility of the flows, final point density required for training can be obtained as a product of the base distribution density and the determinant of Jacobian of the flow transformations. We extend our generative model to a single-view reconstruction model in a manner similar to probabilistic reconstruction networks. Instead of using an unconditional prior, we can condition it on the image features obtained by an additional CNN image encoder. Resulting model can be trained in a completely similar manner as a purely generative one. Now let us switch to experimental results. Firstly, we perform time and memory efficiency comparisons with point flow model based on continuous normalizing flows. We compare a number of parameters in point cloud decoders, GPU memory footprint during training and sampling time per single point cloud, and total training time. For point flow, we estimate total training time by multiplying the average time per iteration we measured with the number of training iterations provided by the authors. DPFnet have more parameters but lower memory footprint, since they do not need to run ODE solvers. Training and sampling time per single point cloud is more than 30 times faster. Total training time is reduced by an even greater factor. We evaluate generative performance on 3 categories from ShapeNet dataset. We compare to related work in the point cloud generation task by training each reported model from scratch using official implementations. We also modified each of the approaches to ensure the same data processing pipelines and the same hyperparameters for common parts of all the models, such as PointNet type point cloud encoders. Our approach demonstrates state-of-the-art generative performance for 3 out of 7 considered metrics for all categories and perform on par, if not better than point flow, while being significantly faster in training and sampling. Next, we consider an auto-encoding task. For point flow, we report 2 results from the original paper and after training for the same amount of time as DPFnet. Different works consider different data normalization schemes. The most frequent are original scale and per shape normalization to zero mean and unit sphere scale. We train all the models with the original data and obtain state-of-the-art EMD metric. Additionally, we show how the results are improved for our model when trained with normalized data. In single-view reconstruction, we compare to recent voxel, point cloud, and mesh-based approaches. DPFnet outperforms previous works in terms of the EMD and is the best in terms of F1 score among point cloud and mesh-based methods. Qualitatively, in both autoencoding and single-view reconstruction, our model output shapes with points being distributed evenly without sharp density peaks. However, at the same time, it captures a bit less details. Thanks for your attention. Our code is available online, and please read our paper for all the details and experimental comparisons.